Welcome to Mrs. Z's Chemistry. In this video, we will be learning about calorimetry, which is a technique used to measure the amount of heat that is transferred from one substance to another. A calorimeter is the device that we use to measure this heat that is being transferred in a chemical reaction or a physical process. The two things that are doing the transferring are the system and the surroundings. The system is the substance that is undergoing the chemical reaction or the physical change. The system is usually the focus of the whole process. The surroundings is the substance that is surrounding the system. Technically, the entire rest of the universe that is not the system is considered the surroundings. So let's look at this concept of the system versus the surroundings a little closer. In this first picture here, we have a calorimeter, and that is being modeled by the gray border. It's a container that's going to hold in the system and the surroundings. You can see in this green circle we have the system, and it's an exothermic process, which is why the arrows are pointing outward, because exothermic processes release or lose energy. Remember that Q is the variable we use for heat/energy, and it's measured in the unit joules. You can see that the heat is leaving the system and going into the surroundings. The surroundings is usually water for a variety of different reasons. You can see that the thermometer is only measuring the surroundings and not the system. For a variety of reasons, we can't measure the temperature of the system usually. So when the system releases energy into the surroundings, you can see that our temperature of the solution is going to increase. And then at some point, both system and surroundings will be at the same temperature. Looking at the next picture, we have two more boxes for a new calorimeter that's going to show an endothermic process. Again, the green circle is the system, and we can see arrows of heat, or Q, pointing into the system from the surroundings. So now energy is being taken from the surroundings and going into the system. And this means the temperature of the surroundings will decrease, as we can see by the thermometer. This is what a calorimeter could look like. It is a container made of good insulating material. Sometimes it's multiple layers of this material. Inside we have the system and the surroundings, and then we have a thermometer that's inside the calorimeter, and we have a stirring bar in case the chemical reactions need to be stirred in order to fully complete. This is something called a coffee cup calorimeter, and it's something you could do at home. It is literally a styrofoam coffee cup with a lid. Sometimes you can put two coffee cups together in order to make the insulating material a little bit better. Inside, we have the system and the solution. We have a thermometer poking into the cup in order to measure the temperature change of the surroundings, and you could possibly have a stirring bar also poking into the cup to make sure the contents get fully stirred. So let's look at this example. We have a capital M right here, and that is for the hot piece of metal. In this example here, we're not going to be looking at a chemical reaction. We're just going to look at a hot piece of metal that's being placed into cold water. The W is representing our cold water. You can see the thermometer is only touching the surroundings or the water. We're not going to be measuring the temperature of the metal. Heat, which is Q, is transferred from M to W, from the metal to the water, until both of them are at the same temperature. And under perfect conditions, which means the calorimeter is perfect enough that no heat is lost to outside the calorimeter, so all the heat is being transferred directly to the water and can be measured by the thermometer. So under perfect conditions, we have Q of the substance M plus Q of the substance W is going to equal 0. If we subtract Q of W on both sides of the equation, this will make a little bit more sense. Now we can say that Q of M is equal and opposite to Q of W. And that's because all of the heat or energy that is being lost by the metal is going to be gained by the water. It actually doesn't matter where this negative sign is, if it's written on one side of the equation or the other. We just need to have it on one side or the other, because one of the things is going to lose energy, the other thing will gain the energy. So let's look at our first example here. A 360 gram piece of rebar is dropped into 425 milliliters of water at 24 degrees Celsius. The final temperature of the water was measured as 42.7 degrees Celsius. Calculate the initial temperature of the piece of rebar. Assume the specific heat of steel, which is the rebar, is approximately the same as that for iron, and that all heat transfer occurs between the rebar and the water, which means there is no heat exchange with the environment outside. So, at first glance, these problems are usually fairly confusing. So let's look at this explanation of the problem. The temperature of the water is increasing from 24 to 42.7 degrees Celsius. So that tells us that the water is absorbing the heat. And all of this heat is coming from the piece of rebar, which was initially at a higher temperature, and that higher temperature is what we're trying to solve for. So assuming that all heat transfer was between the rebar and the water, with no heat lost to the outside environment, then heat taken in by the water is equal and opposite to the heat given off by the rebar. Or, with math, we say Q of water is equal and opposite to Q of rebar. We know that Q is the variable for heat, and it is the equation Cm delta T. So we have Cm delta T for water, and that is equal and opposite to Cm delta T for the rebar. Now, if we plug in all of the numbers that we know for this, we can then solve it, and it becomes an algebra problem. C means the specific heat. So we want the specific heat of water. If you look it up on a chart, you'll see that the specific heat of water is 4.184. The mass of the water from the problem was 425 milliliters. Because the density of water is 1 milliliter for every 1 gram, we have 425 grams for this 425 milliliters. It's important that our mass is in grams because the specific heat has units of grams, and they need to cancel. Delta T is always T final minus T initial. The final temperature of the water, as given by the problem, is 42.7, and the initial temperature of the water is 24.0. Now we have Cm delta T for the rebar. Just remember that there's a negative sign on this side of the equation, which is going to distribute through all of the variables. The specific heat of rebar, the problem says, is the same as that for iron. If you look it up, iron has a specific heat of 0.449. The mass of the rebar is 360 grams, as told by the problem. And the final temperature and the initial temperatures are sometimes a little bit tricky for the rebar, or for the metal. For the final temperature of the metal, we have to remember that if we go back and look at this picture here, at the end, both the metal and the water are going to be at the same temperature because at some point they will have transferred all of the heat and they will be at the same temperature and no more heat will be transferring. So the final temperature of the metal is the same as the final temperature of the water, which is 42.7. The initial temperature of the metal is in fact the variable that we are solving for. Now you can see that this is just a math problem. Use your algebra skills to solve this. Pause and work out this problem. Here is the problem. There are a variety of ways you can use algebra to solve this, but you should come out to 248 degrees Celsius. This answer is a reasonable answer because if you think about it, the water started out at 24 degrees Celsius, which is around room temperature water. And then just by dropping in a hot piece of metal, the water increased to a temperature of 42.7, which is kind of like a warm coffee, or kind of a hot coffee even. So that tells us that piece of metal must have been very hot. At the very least, it needs to be hotter than 42.7. So it's always a good idea to make sure you do a reasonable check with these problems because it's very easy to make a mistake either somewhere in your algebra or a calculator typo. And you miss maybe one of the negative signs or you switch a number and that could drastically change your answer. So do a reasonable check to make sure that you are on the right track or within the same range. Here's problem 6. It's almost an identical problem to the problem we just finished. We just have a different piece of metal, which is copper, and we have different masses and different final and initial temperatures. Pause and work this problem out before moving on. Here is the answer, worked out very similarly to the last problem. Our answer is 335.6 degrees Celsius. Here's problem 7. A 59.7 gram piece of metal that had been submerged in boiling water was quickly transferred into 60 milliliters of water initially at 22 degrees Celsius. The final temperature is 28.5 degrees Celsius. Use these data to determine the specific heat of the metal. Use this result to identify the metal. This problem is a little bit different than before, though we're still going to have Q of metal is equal and opposite to Q of water. So the problem is asking us to solve for, right here, it says determine the specific heat of the metal. Specific heat is C in the equation, so it's the C of the metal is what we're trying to solve for. If we were to divide the M delta T of the metal on both sides of the equation, we would then have C of the metal is equal to this portion of the equation, the negative Cm delta T of the water, divided by the M delta T of the metal. Now, if you plug in all of the numbers that we have from the problem for each of these variables, you should be able to solve the problem. Pause to see if you can work this out before looking at the answer. So we have 4.184, which is our specific heat of the water. And then we have the mass of the water here, and we have the temperature change for the water. That is the final minus the initial, and that equals 6.5. Then we have the mass of the metal, and we have the temperature change of the metal. The temperature change of the metal is often the most confusing portion of it. The final temperature of the metal is equal to the same as the water, which was, if we look back at the problem, that was 28.5. That's the final temperature because both the metal and the water are going to be the same temperature at the end. The initial temperature of the metal is what's the extra confusing part. If you look at the problem here, it is saying, look at where the metal was right before it was quickly transferred into the 60 milliliters of cold water. The metal had been submerged in boiling water. So we can assume that the metal had been in this separate pot of boiling water long enough that the metal was at the same temperature of boiling water. Water boils at 100 degrees Celsius, so that means the initial temperature of the metal was also 100 degrees Celsius. So that would be where this negative 71.5 comes from. It's from this 28.5 minus 100. When you solve this, we should come out to 0.38 for our specific heat, which if you look up on a list, that would come out to be copper. Let's look at problem 8 now. A 92.9 gram piece of a silver gray metal is heated to 178 degrees Celsius and then quickly transferred into 75 milliliters of water initially at only 24 degrees Celsius. After 5 minutes, both the metal and the water have reached the same temperature, 29.7 degrees Celsius. Determine the specific heat and the identity of the metal. Pause and work this out. Here is the problem all worked out, and their end answer is 0.13 for the specific heat of the metal. If you look at a list, you can see that both gold and lead are very close to 0.13. Well, because the problem is describing the metal as silver gray, that means it must be lead and not gold.